Hi, welcome to Understanding Complex Exponentials, Lecture 3, Relation of Complex Exponentials to the Sine and Cosine Functions, Part 1. In this lecture, we'll give the Taylor series expansions of e to the ix, sine theta, and cosine theta, and give the relation between these quantities. We'll show how we represent complex exponentials in the complex plane, and finally, we'll assign some exercises for plotting complex exponentials in the complex plane. The answers to these exercises will be given in the next lecture. In this section, we're going to show how complex exponentials of the form e to the ix are related to the trigonometric functions sine x and cosine x. We will be showing this using infinite series expansions for these functions. We'll then use these relations to show how we can plot complex exponentials in the complex plane. And reminder, if you've had calculus and are familiar with Taylor series, it is recommended that you first watch Lecture 9 before continuing with this lecture. Okay, so the functions e to the x, sine theta, and cosine theta can be represented by infinite series. So e to the x is equal to the sum over n from n equals 0 to infinity of x raised to the power of n over n factorial, which equals 1 plus x squared over 2 plus x cubed over 6 plus etc. Sine theta can be written as the sum over m from m equals 0 to infinity of minus 1 raised to the m power, theta raised to the power of 2m plus 1, all over 2m plus 1 factorial. This is equal to theta plus minus theta cubed over 6 plus theta to the 5th over 120 plus etc. And lastly, cosine theta can be written as the sum over m from 0 to infinity of minus 1 raised to the power of m, theta raised to the power of 2m, divided by 2m factorial. This equals 1 plus minus theta squared over 2 plus theta to the 4th over 24 plus etc. And note here that n followed by an exclamation point, which is read as n factorial, is equal to 1 times 2 times 3 times 4, etc. up to n. Okay, now we're going to see what happens if we take the series expansion for e to the x and set x equal to I theta. Okay, let's take that series expansion of e to the x. So, the sum over n from n equals 0 to infinity of x raised to the n power over n factorial. And now let's evaluate that for x equal to I theta. So we get that e to the I theta is equal to the sum over n from 0 to infinity of I theta raised to the n power over n factorial. This equals 1 plus I theta plus I theta squared over 2 plus I theta cubed over 6, etc. Okay, next let's remember that I squared equals minus 1, I cubed equals minus I, and I to the 4th equals 1. So we can slightly rewrite each of the terms in this series. So the first term, 1, just stays 1. The second term, I theta, just stays I theta. The third term, I theta squared over 2, becomes minus theta squared over 2. The next term, I theta cubed over 6, becomes minus I theta cubed over 6, etc. Note that the terms for even n, so n equals 0, 2, 4, etc., are real, and that those for odd n, so n equals 1, 3, 5, etc., are imaginary. And also note that both the imaginary terms and the real terms alternate in sign. Okay, so let's write e to the I theta as two separate infinite series, one of which is purely real and one that is purely imaginary. Note that even n can be written in the form n equals 2m, where m equals 0, 1, 2, 3, 4, etc. And similarly, odd n can be written as n equals 2m plus 1, where m equals 0, 1, 2, 3, 4, etc. So let's separate out the even n and the odd n terms in the series expansion for e to the I theta. So e to the I theta is equal to the sum over n from n equals 0 to infinity of I theta raised to the n power over n factorial. And now we're going to write that as two sums. So the first sum is the sum over m from 0 to infinity of I theta raised to the 2m power over 2m factorial. And the second sum is the sum over m from 0 to infinity of I theta raised to the power of 2m plus 1, and all of that is divided by 2m plus 1 factorial. Okay, so now let's use the fact that I raised to the 2m power is equal to minus 1 raised to the m power. So we have e to the I theta equals the sum over n from 0 to infinity of I theta raised to the power of n over n factorial, and that equals the sum over m from 0 to infinity of minus 1 raised to the m power times theta raised to the 2m power divided by 2m factorial plus the sum over m from 0 to infinity of I times minus 1 raised to the m power times theta raised to the power of 2m plus 1 divided by 2m plus 1 factorial. Now note that all of the terms in the first sum over m are real, and all of the terms in the second sum over m are imaginary. So we can pull a factor of I out of the last sum to get that e to the I theta, which equals the sum over n from 0 to infinity of I theta raised to the n power over n factorial, equals the sum over m from 0 to infinity of minus 1 raised to the m power times theta raised to the power of 2m over 2m factorial plus I times the sum over m from 0 to infinity of minus 1 raised to the power of m theta raised to the power of 2m plus 1 divided by 2m plus 1 factorial. Now, let's compare this to our expressions for sine theta and cosine theta. So we have that sine theta is equal to the sum over m from 0 to infinity of minus 1 raised to the m power, theta raised to the power of 2m plus 1, divided by 2m plus 1 factorial. And we have that cosine theta is equal to the sum over m from 0 to infinity of minus 1 to the m power, theta to the 2m power, divided by 2m factorial. If we compare our expressions for e to the I theta, sine theta, and cosine theta, we obtain that e to the I theta is equal to cosine theta plus I sine theta. Now this is a very important relation, so we would encourage you at this point to stop and make sure that you understand all of the steps that led to this relation. Okay, so let's get a feel for this by looking at the first few terms in each of these series. So here we've written out the first 7 terms in e to the I theta, the first 3 terms in sine theta, and the first 3 terms in cosine theta. We can see by multiplying sine theta by I that there is an exact correspondence between the terms in e to the I theta and those in cosine theta plus I sine theta. So we can see that if we multiply sine theta by I, the terms in I sine theta correspond to the 2nd, 4th, 6th, etc. terms in e to the I theta, while the terms in cosine theta correspond to the 1st, 3rd, 5th, 7th, etc. terms in e to the I theta. Also, note that the relation e to the I theta equals cosine theta plus I sine theta is only true if theta is measured in radians. Okay, so let's plot the number e to the I theta in the complex plane. First, let's note the real and imaginary parts of e to the I theta. So, the real part of e to the I theta equals the real part of cosine theta plus I sine theta, which equals cosine theta. And the imaginary part of e to the I theta is equal to the imaginary part of cosine theta plus I sine theta, which equals sine theta. So, in the complex plane, the x-coordinate of e to the I theta is equal to cosine theta, and the y-coordinate is equal to sine theta. Now in this plot we have the hypotenuse of this triangle labeled r. What is r? Well, r squared equals sine theta squared plus cosine theta squared. That equals 1. So all points of the form e to the I theta, where theta is a real number, will fall on a circle of radius 1. Shown here in green. Lastly, remember the geometric definitions of the sine and cosine functions. In a right triangle, the sine is equal to the length of the opposite side over the length of the hypotenuse, and the cosine is equal to the length of the adjacent side over the length of the hypotenuse. So we can see in this diagram that the angle that the hypotenuse makes with the positive x-axis is precisely theta. Okay, finally, let's summarize and give some exercises for next time. So in this lecture, we've derived the relation e to the I theta equals cosine theta plus I sine theta using series expansion formulas. We've also covered how to plot e to the I theta in the complex plane, and we've seen that points of the form e to the I theta lie on a circle of radius 1 about the origin and on a line which makes an angle theta with the positive x-axis. Okay, now let's get some practice. Plot the following in the complex plane: e to the I pi, e to the I pi over 3, e to the minus I pi over 4, e to the minus 3I pi over 4, and lastly, e raised to the power of 1 plus I pi over 2. And on that last example, be careful because this is not of the form e to the I theta for real theta. The answers to these exercises will be given at the beginning of the next lecture.